All right, so for part D, where we're talking about the production level that will minimize average cost, again, I'm going to go over to a separate page to work through this, but for the minimum average cost, I will first look at my average cost function. So I can get that average cost function from part B, where I found that my simplified average cost function looks like this. So it's 16 over x to the 1/2 plus x over 1,000. Now, what I need to do with this average cost function is I need to apply the first derivative test. So to apply that first derivative test, I need to first get my derivative, set it equal to 0 or does not exist. So what I would see here is that I would want to rewrite this as 16x to the negative 1/2, bringing that variable up into the numerator, and then plus x to the 1,000 to get ready to take my derivative. So my derivative is going to be bringing down the negative 1/2. It will be 16 times negative 1/2 x to the negative 3/2. Again, negative 1/2 minus 1 is where I'm getting the negative 3/2 because I am differentiating this average cost function. All right, and then I have this plus x over 1,000. That x over 1,000 is a linear term, so its derivative will go to the coefficient. So that will be 1 over 1,000. So simplifying this, the 16 times negative 1 gives us negative 8 x to the negative 3/2 plus 1 over 1,000. And that is my first derivative. Now, with that first derivative, remember we're trying to find our critical numbers. So we need to set our numerator equal to 0 and our denominator equal to 0. So to find the critical number, the first thing I'm going to do is I'm going to move the negative exponent as soon as I possibly can. So that's going to give us negative 8 over x to the positive 3/2, and then plus the 1 over 1,000. Then I am going to get an LCD. Now, to get the LCD here, I have two completely different denominators, so I'm going to multiply those together. So I will have 1,000 times x to the 3/2 as my LCD. So this would be a negative 8 over x to the 3/2. That would need to get multiplied by 1,000 over 1,000, and then plus 1 over 1,000 to get its term to have the LCD. It would need to get multiplied by the x to the 3/2. And then now that I have the LCD, both of them have this 1,000 times x to the 3/2, I can write that as one big fraction where I have 1,000 x to the 3/2 in the denominator. And then in the numerator, I would have negative 8 times 1,000, so negative 8,000 plus 1 times the x to the 3/2. And so then I would set the numerator equal to 0 and denominator equal to 0 as part of the LCD, or as part of finding the critical numbers. So this would give me negative 8,000 plus x to the 3/2 equal to 0. And then over here, I would have 1,000 x to the 3/2 equal to 0. So solving this first equation, I'm going to undo PIMDES. So I'm going to add 8,000 on both sides. And that's going to give us x to the 3/2 is equal to 8,000. And then the way that we undo the exponent is we raise both sides to the 2/3 power. So we raise to the reciprocal. So those cross out and we get x equals. And again, just to be clear, on your calculator, you are going to type in 8,000 and then caret, raise it in parentheses to the 2/3 power. And that gives you 400. All right, now I will say in the previous example, this was true, and this is very true with optimization questions. Usually this denominator equal to 0, usually it's going to give you a bogus answer. Okay, so usually it's not going to generate what I call like a viable critical number that actually minimizes the function. Now, with that said though, we can't take anything for granted. We can't just assume, oh, it's going to give us something that's like not going to really work for us. But just kind of keep that in mind, like as you're working through this, that, yes, like you're going to set the derivative does not exist. But the thing is usually this comes from, or usually generates a critical number that is an endpoint of the domain, and that causes an issue. That means it's not really a critical number, and that also means that it's probably not going to minimize the function. So again, we're going to go through this, but usually you're going to see that it doesn't really end up with anything that generates the critical number that works for you, at least. So we divide both sides by 1,000, and we get x to the 3/2 is equal to 0. And then just like we did over here, to undo that power, we raise both sides to the 2/3. And that gives us x is equal to 0. Now, if we did not have this, like, well, I don't know if that's actually a critical number or not, what we would do is we would go over to the next page. There's a lot of multi-page problem here, but we would go over to the next page and we would work through our number line. So what we're finding here is that we think that 400, 0 are the two critical numbers. Again, this is if we didn't spend any time working with the domain at the beginning of the problem. So if I do that, I'm going to have this 400, I'm going to have 0, and then I'm going to have 400. Okay, so with that in mind, what we will see is that we need to plug into the derivative. So the f prime, right before we set numerator equal to 0, denominator equal to 0, that f prime was given here. So we're going to plug into the 8,000, negative 8,000 plus x to the 3/2 over 1,000 x to the 3/2. All right, so I plug in the negative 8,000 plus, and then maybe I decide for this first one I'm going to plug in -1. So -1 to the 3/2, and then over 1,000 -1 to the 3/2. That's going to give us a negative over a positive. So overall, we get a negative. Then we will plug in from 0 to 400. Maybe we plug in 1. That is also going to give us a negative because it will give us a negative in the numerator over a positive. And then we plug in the 400, maybe we plug in 402. So we get negative 8,000 plus 402 to the 3/2 over 1,000 times 402 to the 3/2. And that is going to give us a positive over a positive. Again, as always, just really be careful with the plugging in here, the negative 8,000 plus 400, and then make sure you caret and then parentheses 3 divided by 2. Make sure you put parentheses around that exponent. And again, I'm not plugging in 400, I'm plugging in 402, and that's going to give us a positive. So we have a positive over a positive, so we get a positive overall. So we get a decreasing, decreasing, and then increasing, and so that tells us that 400 is our critical number that will minimize the production level. So our answer here will be minimizing average cost is 400. And then to find that minimum average cost, we will simply plug in to the average cost function. So again, my average cost function was the 16 over x to the 1/2 plus x over 1,000. And again, that's from part B. We're plugging into that original function, not the derivative, but the original function. And that will give us 16 over 400 to the 1/2 plus 400 over 1,000. And that will round to just 1.2.